The behavior of dielectric materials in an electrostatic field was already studied by Faraday. In 1837 he showed in his experiments that if the space between the plates of a capacitor is filled with some insulating material instead of vacuum or air, then the electric capacitance of the capacitor increases. That is, if C0 is the capacitance measured for a parallel plate capacitor with a vacuum or air between its plates, when the charges plus Q0 and minus Q0 on its plates produce the electric field E0 in the capacitor, then the capacitance C measured for the same capacitor storing the same amount of charge but with insulating material between its two plates that produces the electric field E, is greater than the capacitance C0. Electrical insulators or dielectrics are materials that do not conduct electrical current, but such ideal insulators do not exist in nature. All substances conduct electricity even if to a negligible extent. In general, metals conduct electricity 10 to 15 to 10 to 20 times better than the materials called dielectrics. When we introduced the concepts of electrical conductors and insulators, we mentioned some examples for electrical conductors in everyday life, such as metals, the human body and the ground. For electrical insulators, we mentioned glass, ebonite and amber. The list of substances insulating electricity is of course more extensive. Besides glass or ebonite, we can talk about rubber in a more general sense, plastic, wax, wood, air, ceramic, styrofoam, and so on. We already had a discussion on the quantized nature of electric charge, and established that electrons and ions are charge carriers. Hence it is easy to see that the properties of electrical conduction and insulation are the result of electron mobility in materials. Conductors contain abundant valence electrons in their chemical bonds that can move easily from one atom to another when voltage is applied, producing an electric current in the material. As opposed to conductors, insulators have electrons tightly bond to a single atom and impede from free flow of electrons from atom to atom. These fundamental differences in the atomic or molecular structures of different substances indicate that the effectiveness of electrical insulation depends on the inherent properties of the material. At the same time, it also depends on the voltage applied on the substance and environmental factors like temperature, moisture, contamination, aging and so on. All of these factors can degrade the performance of dielectric materials and cause electric breakdown. As already mentioned in the discussion on capacitors, only the maximum breakdown voltage can be applied on a capacitor without causing an electric breakdown of the dielectric material between its plates. This phenomenon also indicates that if a dielectric is introduced into the electric field of a charged capacitor, changes usually occur both in the electric field and in the dielectric itself. Motivated by these findings, let us first examine how the capacitance and the electric field of a capacitor change as a result of placing a dielectric into the electric field of the capacitor, under the condition that the charge or voltage of the capacitor is constant. Let us start with the experiment examining how the capacitance and the electric field of a parallel place capacitor alter as a result of a dielectric placed in the electric field of the capacitor, under the condition that the charge of the capacitor is constant. First we connect an electrometer to the plates of the parallel plate capacitor with a vacuum or air between the plates, and bring the charges plus Q0 and minus Q0 to its plates. This given amount of charge produces the electric field E0 in the capacitor, and the voltage V0 is indicated by the electrometer. If we insert a paraffin block between the metal plates of the capacitor, then the electric field must change between the plates of the capacitor denoted by the letter E, since we find that the electrometer measures a voltage V that is less than the initial value V0. After removing the paraffin block, the initial voltage V0 is measured between the plates of the capacitor again. Considering that the amount of the charge Q0 on the plates remains the same during the experiment, the electric capacitance of the capacitor can be expressed in two forms according to whether there is a vacuum or air, or an insulating material between the plates. In the case of a vacuum or air, the capacitance C0 of the parallel plate capacitor is equal to the ratio of the charge Q0 to the voltage V0. For the capacitor with a dielectric between its plates, the capacitance C is given by the ratio of the charge Q0 to the voltage V. Since the experiment shows that V0 is greater than V, we conclude from the comparison of the two equations that the capacitance C is greater than the capacity C0, that is, the capacitance of the parallel plate capacitor is increased by inserting an insulating material between its plates. According to the measurements, if the insulating material completely fills the space between the plates of the capacitor, the ratio epsilon R of the capacitance C to the capacitance C0 is independent of the type and size of the capacitor and only depends on the given insulating material. The ratio epsilon R, which is greater than 1, is called the relative dielectric constant or the relative permittivity of the material. So this is a mere number that gives how many times the capacitance of a capacitor filled with dielectric is greater than the capacitance of a capacitor with a vacuum or air between its plates. By definition, epsilon r is equal to 1 for vacuum. The following table shows the relative dielectric constants of some substances. It can be seen from the table that atmospheric gases and gases in normal state in general have a relative permittivity close to 1. This explains why the gases in normal state hardly affect the electrostatic phenomena that occur in a vacuum. As we have already stated, the capacitance of a capacitor with a dielectric material is epsilon r times greater than its capacitance with a vacuum between the plates. We will also derive analogous relations between the voltages V and V0 and the electric field strength E and E0 with and without insulating material between the plates of the capacitor. Based on the condition of a constant amount of electric charge in the experiment, we can take into account the equations written for the capacitances, use the relation stating the capacitance is given by the ratio of the charge of the capacitor to its voltage, and express the relative dielectric constant by the quotient of the voltages of the capacitor. That is epsilon r is equal to the ratio of the voltage V0 measured for a vacuum or air, to the voltage V measured for the dielectric. If E0 and E represent the electric field strengths between the plates of the parallel plate capacitor in the case of a vacuum and an insulating material and D is the distance between the parallel plates of the capacitor, then the voltage V0 can be expressed by the product of the magnitude of the electric field strength E0 and the distance D, and the voltage V is equal to the magnitude of the field strength E times the distance D. These equations are derived from the fact that the electric field is uniform between the plates. As a result, the relative dielectric constant epsilon r can be written as the ratio of the magnitude of the electric field strength E0 to the magnitude of the electric field strength E. This formula indicates that if the charge on the plates of the parallel plate capacitor creates an electric field with the field strength E0 in the space between the plates in a vacuum or air, then the same amount of charge creates a weaker electric field with the magnitude E in the dielectric, that is, a field strength is epsilon r times smaller than the field strength in a vacuum. This result obtained for the field strength in the case of this experiment with special conditions is also true in general. That is, the electric field strength due to any system of charges placed in a vacuum decreases everywhere if the space is filled with a homogeneous and isotropic dielectric of the same dielectric constant, while leaving the charges unchanged. Because in the formulas describing electromagnetic laws, epsilon r occurs in a product with the vacuum permittivity epsilon naught, it is reasonable to introduce the absolute dielectric constant or absolute permittivity epsilon as the product of the two quantities. Since the relative permittivity is just a number, the unit for absolute permittivity is the same as the unit for vacuum permittivity, which is Coulomb squared per Newton meter squared. Now we modify the conditions of the experiment in such a way that a constant potential difference V0 is maintained between the plates of the parallel plate capacitor with the help of a battery, while the electrometer is switched into the mode measuring electric current, that is the rate of the flow of electric charge described by the time derivative of the charge. In the case of the capacitor with the paraffin block, that is a dielectric between its plates, the charge Q of the capacitor is given by the capacitance C of the capacitor times the voltage V0 maintained between its plates. In the previous experiment with a constant electric charge of the capacitor, we found that the capacitance C of the capacitor is equal to the relative permittivity epsilon r of the insulating material filling the space between the plates, times the capacitance C0 of the capacitor with a vacuum or air between its plates. In this experiment the voltage V0 through the capacitor is kept constant while the amount of charge on the plates of the capacitor is different in the two cases. For the capacitor with a vacuum or air between its plates the charge Q0 is given by the product of the capacitance C0 and the voltage V0, whereas we can express the capacitance C in the formula of the charge Q of the capacitor filled with a dielectric between its plates as the relative permittivity epsilon r of the dielectric, times the capacitance C0. Then the charge Q is equal to the relative permittivity epsilon r times the charge Q0, where epsilon r is greater than 1. This formula shows that the charge of the capacitor increases from Q0 to Q by filling the space between its plates with an insulating material. The measurements in the experiment confirm this result. When the dielectric is inserted between the plates of the capacitor, the electrometer indicates a transient electric current in the circuit. If the time of the transient flow of electric charge during which the paraffin block is inserted between the plates is known, then the change in the charge of the capacitor from Q0 to Q can be determined. We will find that the electric charge of the capacitor after inserting the paraffin block between the plates is epsilon r times greater than the charge of the capacitor with a vacuum or air between its plates. Because the voltage is constant during the experiments, the electric field strength E0 does not change between the plates of the capacitor even in the presence of a dielectric material. Then the magnitude of the uniform field E0 is given by the voltage V0 times the distance d between the plates, and we can write that the magnitude of the electric field strength E is equal to the magnitude of the electric field strength E0. The relationships obtained for the electric charge and the electric field strength express that if a given amount of charge of a parallel plate capacitor produces an electric field strength in a vacuum or air, then the same field strength in a dielectric between the plates of the capacitor can be produced by epsilon or times greater amount of charge on the plates of the capacitor. Experiments show that the capacitance of any type of capacitor with a dielectric between its plates is epsilon or times greater than that of the capacitor with a vacuum or air between its plates. Specifically, the capacitance of a parallel plate capacitor, when the space between the plates is filled by an insulating material with a dielectric constant epsilon r, is described by the product of epsilon r and the capacitance C0 of the capacitor with a vacuum or air between its plates. The latter is equal to the dielectric constant epsilon naught of a vacuum, times the ratio of the surface area A of each plate of the capacitor to the distance d between the plates. It is generally true that the capacitance C of an arbitrary type of capacitor can be written as the vacuum permittivity epsilon naught times the relative permittivity epsilon r of the dielectric material filling the space between the plates of the capacitor, times a factor L with a unit of length depending on the geometry of the capacitor. That is, the capacitance C of the capacitor is equal to the absolute permittivity epsilon of the dielectric material used for the capacitor, times the geometric factor L of the capacitor.